Hello everyone. Today I want to talk about how reduced echelon form allows us to describe solution sets to systems of equations. So just to recap where we were, so given an m by n system, so this means m equations in n variables, we perform these row operations. So first you go left to right, top to bottom, to obtain the echelon form. So this is also maybe just triangular is sometimes what people call it. And here we can determine at this point, you can determine if a solution exists and actually how many. And I'll remind you of that in an example in a second. But then after you do that, so if you want to know more, right? So at this point we know if the system has a solution, and I can actually tell you how many there are if they do exist. But if you want to go right to left, right, bottom to top, this is how we clear pivots above, we clear above pivots in this case. This is how we get the reduced echelon form. So this is clearing above pivots. So the left to right was clearing below pivots. I could say that here. This is clearing below pivots. And when we go right to left, when we clear above pivots, this provides a description of the solution set, which is what I want to talk about today mostly. So let me do this with an example. So let's maybe start with this guy here. So let's consider a 3x3 system. 1, minus 2, 1, 0, 0, 2, minus 8, 8, 5, 0, minus 5, 10. So this is a 3x3 system, right? I have 3 equations, 3 unknowns. And if I press my kind of magic row reduction button, you do your, right, so this would be my first pivot. If I clear below that, I keep going. What I get eventually is the following. So this is one version of a echelon form. Okay, so I've now identified my 3 pivots. I actually have these 3 pivots. And notice, right, at this point, I can tell that since I never have a 0, 0, 0 non-zero, right, there's always, in every row I have some non-zero thing to the left of the augmented part. This actually tells me that the system is consistent. And in fact, right, there's a pivot in every column, This will tell me that there's no free variables. So I have no choice of how to assign a certain variable a certain number. So this implies that not only is the system consistent, the system has a unique solution. So there's a unique way to choose x1, x2, and x3 that works for those 3 equations there. Now what is that solution? Well, that's where the reduced echelon. So to find that solution, bring this down. To find that solution, we reduce to reduced echelon. And again, I'm going to press my magic button to spare you the calculations here. But if you take this matrix here and you start reducing above the pivot, so first I would probably scale that by minus 1/10 to get it to 1. But if you do that, what you get is the following. So if you perform your row operations, you get this. This is reduced echelon form. And what is this telling me? Well, you notice that in this, this is the whole idea, is that reduced echelon form is sort of the best way to describe your system. It's the most sort of convenient way to describe the system in the sense that you can read off solutions. And in this case, you really can easily read off, because what is this saying? I mean, this is literally just saying that x1 equals 1. That's the first equation. Second equation is saying x2 equals 0. Third equation is saying x1 equals minus 1. So there you go. That's the solution. So the unique solution is going to be, we usually write this as 1, 0, minus 1, right? I want to put the x1 first, the x2 second, the x3 last. And so that's the answer, right? And again, just to recap, I knew, given the matrix, I reduce it to echelon form, just clearing below pivots. I know that the thing is consistent, and in fact, there's one solution. If I want to know what that solution is, I go to reduced echelon, and I can just read it off now. x1 is 1, x2 is 0, x3 is minus 1. I'm done. Let's do one more, maybe slightly more interesting example, or more complicated at least. Let me use that example from last lecture. Let's consider what that was, a 3x5 system. Let me actually just write it out just to have it in front of me here. So it's 5 variables. This was the first equation. Then I had these. Six, I guess, and then 15. Okay, so this is a 3x5 system. I have 3 equations, 5 unknowns. And again, I'm going to press my magic row reduction button, clear below pivots. Actually, remember in the example, I actually had to first swap row 1 and 2 because I wanted that pivot to be in the upper left corner. But regardless, if you do this, let's see, did I write this out somewhere? Yeah, so it's 3, minus 9, 12, minus 9, 6, 15. Looks like I swapped row 1 and 3 here. Something like this. And I had 0, 0, 0, 0, 1, 4. Okay, so this is now echelon, right? Because here are my pivots, right? Remember, the pivots are the leading entries in every row. So the first non-zero entry that I see when I'm in echelon form. I have pivots in every row now, right? And there's no rows that have just zeros with something non-zero. So again, this is telling me this is consistent. Okay, so it has a solution, but how many are there? Well, there's pivots in columns 1, 2, and what is that, 5. So this is telling me in particular that there are free variables. So this also implies that the x3 and x4 are free variables. So what this means, I'll explain more in a second, but this means that I can assign anything to those 2 variables. They can be anything. They will determine the values of x1, x2, and x5, the others. And so what this is telling me is that not only is it consistent, but there's infinitely many solutions. And again, I could say all of that just from looking at the echelon form. And as we saw before, to actually describe those solutions, we go to reduced echelon. So just like we did before in that last example, so to describe those solutions, go to reduced echelon. And again, to spare you the calculation, I'm just going to tell you what that is in this case. So it looks like it's something like this. So it's 1, 0, minus 2, 3, 0, minus 24. 0, 1, 2, what's minus 2, 2, 0, minus 7, 0, 0, 0, 0, 1, 4. Okay, so notice this is reduced echelon. How do I know that? Well, not only have I cleared everything below the pivots, right? These are, again, the pivots. Zeros below the pivots, but also zeros above, and also the pivots themselves have value 1. That's how I know it's reduced echelon. Okay, so how do I now go about describing the solution? Well, it's going to be a little bit more complicated because I know there's infinitely many. But again, let me just write down that x1, x2, and x5 are pivot variables. x3, x4 are free. So what we're going to want to do is we're going to describe the pivot variables in terms of the free. Okay, what do I mean by that? Let me do that kind of by example again. So what I do now is in some sense, I'm going to go from the bottom to the top here looking at those equations. So equation 3 now says, well, that's pretty easy, right? It's just saying that x5 equals 4. So x5 is a pivot variable, and actually I know how to describe it fully, right? It has to equal 4. So in some sense, I'm describing pivot variables in terms of free. Well, this one doesn't even need any frees to describe it. Okay, well then again, x4 is free. This is what I said before. x3 is free. And then I go to the next pivot, right? I go to the next row because it has a pivot. So this is telling me that x2 minus 2x3 plus 2x4 equals minus 7, right? So can you see all that on the screen? I've solved, well, I've just written down the equation 2, but what I want to do now is solve for the pivot variable. So this means that x2 is equal to minus 7 minus 2x plus 2x3 minus 2x4, right? So I've solved for the pivot variable in terms of the frees. Okay, I've described x2. Now I keep going. So for x1, that's in a pivot row. So I write down that equation. It's x1 minus 2x3 plus 3x4 equals minus 24, right? This is just, I could have said this is equation 2. This is equation 1. Okay, and then I do the same thing. I solve for that pivot variable. x1 equals minus 24 plus 2x3 minus 3x4. Okay, and so that's my solution. This is what this is saying then is that once x3 and x4 can be anything they want, but once I tell you what they are, x1, x2, and x5 are all forced, right? They're all described as well. So somehow the solution is probably this in the, I'll call that a circle, the thing I've circled here. So just, for instance, if I wanted an actual solution, I could choose, say, well, I could take x3 to be, say, 0, and I don't know, x4 to be 1. And then to get what we'd get from there is a solution, well, what would it be? So x1 would then have to be, can I do this in my head? So if x3 is 0, this goes away, x4 is minus 3, so then this would give me x1 is minus 27, if I did that correctly. x2 would be, well, let's solve it here. So again, x3 is 0, x4 is 1. So it looks like minus 7 minus 2 is minus 9. And then we know what x3 is. We just said it's 0, right? We chose it to be 0. x4 we chose to be 1. And x5 we know always has to be 4. So the solution I would write as minus 27 minus 9, 0, 1, 4. Okay, and that's my solution. And again, what I'm doing here is I'm giving you the recipe to describe all possible solutions with the idea is that x3 and x4 can be anything. They're arbitrary. It forces the other ones, and it gives me a recipe to describe all the solutions. Now, I should say, just as we're closing up here, that the reason that this, what makes all this tick is that the reduced echelon form of a matrix is unique. There's one and only one way. So no matter how you choose to do your row operations, I'm always going to get to the same reduced row echelon. And so therefore, when I describe my solution this way, it's always the same, right? It better always be the same no matter what moves I make to reduce things. And in fact, that is an important theorem of what's going on here. So that's it for now. We'll see you next time.